Jessica, I had a question about the midterm, just because the calendar um, still just goes to Thanksgiving break, and I was wondering if the midterm is going to be later than like the 6th.
Okay, that I do want to start by talking about that. So
Oh, sweet.
um,
Okay.
we can just kind of go ahead and start there and see. I'll put out an announcement probably too about this.
Okay.
So people who are still joining can see. But did, I was thinking today a bit about the schedule. And I realized, first of all, there are too many of you to do student presentations in 2 days. So I've expanded that one day. I think we can fit pretty much everyone in. They'll be short, but hopefully that's not a huge, I think it'll be like 10 minutes per presentation and we'll just have to move. Um, Hopefully soon I'll have more information on what I want that to look like. Sorry. But because I've done that, what I decided to do was that I took out a day for the midterm. So now we still have some review time, but we won't have a class period for a midterm. So that just means that it'll be kind of like a homework assignment. I'm getting it put together. It'll be through Canvas. My plan is for it to have about 8 questions, and I will make it available on Wednesday the 30th, and then it'll be due, I think, on Thursday the 8th. So you'll have a week to do it, and it'll be, once you start it, you'll have 4 hours to finish. It should not take you 4 hours. The 4 hours is to just have extra time. I don't want you to feel rushed. There will be 8 questions. So yeah, the 4 hours is more if you have a question while you're doing it and you need to get in touch with me and it's taking a long time. Other thing that should be available to you now on that note is in the files, there is a study guide. So this is pretty brief. It has some of what I just said. So I think I think this is consistent with what I just said. Based on what we all decided, the test will be, each test will be 12.5% of your course grade. Open notes, open book, open internet, I don't care. I just don't talk to anyone else about it, please. So do your own work, but research however you want. I don't think I'm writing the questions myself, so it's not like they're online somewhere. And then I've just kind of gone through what we've covered so far and kind of what I hope you took away from my lectures. So this is going to be something to maybe check out at some time before next Tuesday. And then next Tuesday, we will have time where I will put together some sort of little fun competition quiz thing as a review. Hopefully it'll be semi-fun. And there will also be time to ask me questions both about this test and about the photometry project. So there will be time, if you're still finishing up, if you're stuck somewhere, that's a time where you can come bug me about it. But that's my thought. I guess the other thing I can say just on the test, because I want you to do some math, my idea is it'll be on Canvas so I can time it, but to make it hopefully easier, I don't know, there'll be some questions that will have a file upload where you can do the math on paper, take a picture of it, and upload the file. So I think that's the easiest way to do it. If any of you guys are doing things in other classes that you're like, this is better, please tell me. I am trying to figure this out the best I can, but hopefully it's not something that'll be super stressful. And like I said, open note, open book, open internet, just closed classmates. So there won't be class time, but you'll have a full week and 4 hours once you start. So any questions about any of that at the moment?
Do you have any idea about what ratio of the test is math? Is it like mostly writing, a little bit of math, like half math, half writing, or mostly math?
That's a good question. I am still working on the test, so I don't have a full answer. I think it will probably be heavier on the writing side than on the math side, just because we haven't done a ton of math related stuff. So it should be a little bit more focused on interpretation and that. I will note the last point down here is about coding. So we've been doing a lot of coding. So there's a potential that I will give you some code and kind of ask you when you would use it and what it does. I will not ask you to write code. And also you will have access to all of your notebooks. So don't feel like you have to memorize stuff. Just know that there'll be some analysis, a small amount of math, and a small amount of like potential discussion of code. It's kind of what I see. Any other questions?
On the syllabus for the presentations, the last day is on the 21st, but that's a Saturday. Okay.
That is a typo.
Okay.
I meant to fix that and I didn't, because I noticed it and I didn't fix it. So yeah, sorry about that. Someday I'm gonna actually get all my dates right.
And are we doing something on our actual finals period day, the December 3rd?
So there will be a final.
Okay.
I think you won't need to do it at that time. It'll probably look similar to this test where I'll give you time to do it. And if you want to use that in-class finals time, do it then. If you want to do it some other time, do it some other time. I'll probably try to be available on Zoom in that time. But there won't be like, come somewhere and do something. I don't know how any of this is supposed to work. Sorry. Just all doing our best. Any other questions? Sweet. And like I said, I'll send out an announcement after this class that just has that study guide in it and just essentially what I said. So you can, if you didn't get it all as I talked. But today we're time for astronomy. Now that that's out of the way, today we're going to talk about the phases of the ISM and what that means. So ISM is interstellar medium. So it's just the stuff that's between stars and galaxies. And this is just, this image I threw in here is kind of getting at what that means from a kind of solar system view. I always think it's interesting to think about where our solar system ends. So there's jokes about how many times Voyager 1 has left the solar system, because every few years someone says it leaves again, because it travels through a different layer where we say the boundary of our solar system is. So it's crossed the boundary of our solar system about 10 times in the past few years. So just because we don't know where the boundary of our solar system is. So some people like to think that it's where the solar wind stops. Some people think it's this heliopause, which has to do with the sun's magnetic field, but you can argue Oort cloud is way out further. But once we get outside of the sun's influence, we're into interstellar space, and interstellar space is filled with the interstellar medium. I'll just mention this briefly. There's also, you might see the IGM. The IGM is the intergalactic medium. So that's going to be the stuff between galaxies, typically in a galaxy cluster. So the ISM and the IGM are two different things. Interstellar medium, you're inside of the galaxy. Intergalactic medium, you're outside of galaxies. Before we get into that, though, too far, I wanted to just take a little bit of time to review something that what we did in the last class. So when we did the PSF smoothing, a lot of folks were a bit confused about why we were going to do it. And instead of answering you each individually, I thought I would just talk about it as a class. And so I saw a lot of really interesting answers where people were trying to explain why we should. They're like, oh, maybe it gets rid of bad pixels. And like, maybe, but really PSF smoothing does make your image worse. So why you would do it, it might seem a little counterintuitive. You're bringing a high resolution image down to a lower resolution image. The main point, the main reason we do it is because if we're working with multiple images, multiple wavelengths, and also multiple detectors often. So as an example, this is a Hubble image and a Herschel image of the antenna galaxy. Hubble's looking at optical, Herschel is going to be looking at infrared, and what we can see is the resolution of the Herschel image is much, much lower than the Hubble image. So if we were to do aperture photometry in this circle, on the nucleus of the antenna galaxy at both our optical and our infrared, we would be measuring two different things. Because in the infrared, we're getting this kind of blurring in, this bleeding in of light from the arms that we wouldn't see in the Hubble image because it has a higher resolution. It's impossible to bring something from a low resolution to a high resolution. You just can't really do that without making up data, essentially. But with smoothing, we can bring a high resolution image down to a lower resolution image. So we can blur out this Hubble image a little bit using that PSF smoothing. So we're working with apples to apples. We're comparing the same light from these galaxies, whether we're looking at the optical in the Hubble or we're looking at the infrared with Herschel. So the reason why I want y'all to do it is because the second half of your homework, where we're going to focus on spectra, part of it's going to be doing some SED fitting. So SED we'll talk about more in after 4-day. It's spectral energy distribution, and you're going to all make something that looks like this, which is cool. So I'm going to give you some extra data. This is an SED fit I did for potentially one of your galaxies, NGC 3521. And what we can see is that we're able to fit information to photometric points. So we're able to get a whole spectra by fitting a model to our data, the actual photometric data we get, because spectra are harder to get than photometry just because you're looking at every wavelength, so it's going to be fainter than looking at a big chunk of wavelengths. And when we do SED fitting, we can get all kinds of information about a galaxy. We can get star formation history, we can get amount of dust absorption, we can get an H2 mass. So it's a really, really powerful tool, and I think it'll be a good experience for you to try it. But the issue is we're working with a lot of different data points here. So over here, you've got some UV data. You guys are pulling out your UGRIS data, so that's going to be these data points here. And then I'm going to give you a whole boatload of infrared data. And this furthest data point way over here is at 250 microns. So compared to the, a few hundred nanometers that the UGRIS is at, the 250 microns is much longer, which means it's going to have really poor resolution. So to make sure we're looking at the same thing, both at the UGRIS and at the 250 microns, I've asked you to do PSF smoothing. If we were only looking at SDSS data, we would not do that. It would not make sense. But since we're looking at multiple wavelengths, multiple detectors, we're going to use a lot of different bands. We need to make sure we're smoothing so we're getting the same resolution in every image. So that's why we do smoothing. Any questions there? Cool. And you don't need to worry about this yet. I'll have information on this homework assignment up soon. But it's obviously don't try to get started yet. Okay. So just a little final bit of review for y'all before we jump into new stuff. Last week I said PDRs were like onions. Why did I say that? What did I mean? And why are PDRs this way? not going to call in a name, but when someone thinks they have an answer, is willing to share with the class, if you could unmute yourself and just yell out.
They have layers.
Yeah, so exactly. So, and why do they have layers?
Don't different molecules or things dissociate at different temperatures? And so the high energy photons dissociate different things at different like regions.
Perfect, exactly. So thank you, Sabrina and Erin. Our PDRs have layers like an onion. And so if we were thinking about this, maybe this is our H2 region in the center, our core, and then we get atomic hydrogen, sorry, I had to get the right one, but ionized carbon and maybe still, and then we step out, we lose ionized carbon, and now we're starting to get CO as you kind of step out in your layers. So perfect, and just to show that again, if you look at a PDR and measure the ionized fronts, you can see layers as you step out. Awesome. Okay. So now new material. Sorry, that was a bit of review. So I said we were going to talk about phases of the ISM. But first I just want to think, like, typically when we think of phases, we might think of solid, liquid, and gas. Nowhere is the ISM solid. Like, there's not a chunk of material rotating around. It's all pretty much gas with some dust particles, but it's not like giant clumps of dust, and it's not going to be liquid anywhere either. It's mostly going to be gas. So what might I mean when I say a phase? How might we interpret phase here?
Like maybe a relatively homogeneous subsection?
Yeah, so we're going to split up, instead of by solid, liquid, and gas, we're going to look at properties of the ISM and use that to split up into phases. So specifically, the properties we're going to think of, the homogeneities, oh my gosh, if I can talk, are going to be, we're going to look at energy, and we're going to look at density. So energy or temperature, and then the density in that gas. So instead of splitting, so there's kind of, some people talk about different ways of dividing the phases of the ISM. I'm going to do 6. 6 is kind of the most you're going to see in terms of division of phases. Some people will do less. So if someone says there are only 3 phase, I have a 3-phase model of the ISM, they're not leaving out stuff, they're clumping some of these phases together. So just as a little bit of a warning as you go out into the world of astronomy, if you see something different, that's why. 6 tends to be the most you will see, though. I have never seen higher than 6. And it's mostly going to be based on the properties of hydrogen in that phase. So what is hydrogen doing in this in these conditions in the ISM? This is because hydrogen makes up most of our ISM. So 91% of the particles in the ISM are hydrogen. That's just because there's hydrogen is the easiest element to make, so there's a lot of hydrogen in the universe. But even though it's 91% by number, it's only about 60 to 70% by mass. So because hydrogen is so light, even though only about 10% of the ISM is helium, it's about 30 to 40% of the density, depending on which model you'll look at, or 30-40% of the mass, sorry. There's also small amounts of carbon, nitrogen, oxygen, and other heavier elements, which we will see as we move through our layers. But because hydrogen is the most prevalent, we use it to characterize the different phases. So I'm just going to kind of walk through each of these 6 phases and how we might detect or measure what's happening in those phases. So our first phase is the molecular phase. So hydrogen is in its molecular form, sub-2 molecular hydrogen. This is pretty much just going to be GMCs, so we've already kind of gone over what's happening there. It's going to be cold, because otherwise hydrogen will be bumping into things and will disassociate and form atomic hydrogen. It's fairly dense though, so we have or relatively dense. So this is the densest phase of the ISM at about 100 to 1,000 particles per cubic centimeter. So despite the fact this is the densest phase of the ISM, those densities are pretty similar to the best terrestrial vacuums. So the best we can do on Earth, the lowest densities we can get on Earth, are the densest areas in the ISM, approximately, which is kind of interesting.
I have a question.
Yeah.
Is it also structured like an onion where it's got these different layers, or are these kind of just like patches of different regions?
It's going to be more patchy. So our clouds are going to be distributed throughout the disk. So all of these phases are most, with the exception of the last one, this is all going to be in the disk of the galaxy. Molecular clouds are gravitationally bound, so they're a little special, but they're just going to be kind of clumps within the disk. So not necessarily layers, and more of just different clumps. But good question, Ethan. So yeah, so density. The other thing, potentially new term, hopefully not too crazy, we can talk about filling factors for each of these phases. So these are the volume of the ISM that is filled with this phase of gas. So the molecular phase is only fills about 1% of the volume. So these clouds, they're really dense, they're scattered throughout the disk, but they're only about 1% of the volume. So really low in terms of volume, but because they're so dense, they're about 40-ish% of the mass of the ISM. So most of the mass in the ISM is in this phase, but it takes up only a very small percentage of the volume. And then again, it's mostly hydrogen, but there's also some carbon and oxygen. We'll see formaldehyde. Every once in a while, you'll get an article somewhere saying there's alcohol in between the stars. And that's because there's ethyl alcohol, but it's not like, you know, beer. I can tell you, I'm gonna, real quick bad story. I don't know if like, are astro parties still a thing? Do you guys still, I mean, when coronavirus is not happening?
Yes, sometimes.
Cool. So we had some pretty, we went hard at astro parties. And when Nathaniel taught us about the ISM, he mentioned that there was alcohol, potentially things similar to rum, and that it smelled like raspberries, and there was cyanide, and cyanide smells like almonds. And we're like, that sounds like a good drink. We should have an astro party and drink this. It was not good. It was not good. Someone chipped a tooth. I was sick for like 3 days. If you make an ISM drink, do not make it as alcoholic as we made it. It was bad. But anyways, that's my little, there's alcohol in the ISM, but not the kind of alcohol we drink. Tiny side note, because molecular hydrogen doesn't emit light very well, so jumping right back in, smooth transition there, sorry. We instead measure the molecular gas with CO transitions. So just really briefly, we're gonna do a tiny bit of quantum mechanics. So we had our fun story, now we're gonna get into some less fun, in my opinion. Quantum mechanics scares me. But to talk about what CO transitions are, because they are important at this phase. So we're gonna start by thinking about a carbon monoxide molecule as just one carbon and one oxygen. We can kind of think of them as bound together. Simplified model, obviously, but we can kind of model them as bound together by an invisible massless rod. And as they rotate, they emit different light depending on the rotational transitions they go through. So using classical mechanics, we would write the rotational energy as the moment of inertia times the angular velocity squared over 2. So this is like 1/2 mv squared, except in rotational speak. So angular velocity and moment of inertia instead of mass and velocity. And we can write the J levels as the moment of inertia times the angular velocity, angular momentum, velocity squared, or just not squared, sorry. And then the moment of inertia for 2 solid objects bound together is going to be the mass times the radius squared divided by the sum of the masses. So this is just classical mechanics where we're going to start. Now we're going to add some quantum mechanics, which means our J transitions are going to be quantized. So instead of J equaling the moment of inertia times the angular velocity, we're going to write it as this kind of gross equation here, where we're transitioning from the jth energy level to the jth plus one energy level. I cannot say that, I'm sorry. Because that's how quantum mechanics works, everything's going to be quantized. So we can plug that in, doing a little bit of algebra to, instead of writing the rotational energy as this, write it as J squared divided by 2I. That's just because if you square J and divide it by 2I, you get this equation. So that's all, that's just an algebra step. And then plugging in our J formula, we can rewrite that again. So it looks like this. We want to find the frequency of these transitions because that's what we're going to be observing. So I was lazy and just did a V instead of a nu because they didn't look any different in Google Slides. I'm sorry. But that's going to be the change in energy divided by H when we have a transition between our 2 J levels that is probably going to be equal to 1. So delta J going from 1 to 0, 2 to 3 are pretty typical. So these are just the different rotational energy levels. Your J of 1 is going to be, J of 0 is the lowest energy rotational level, J of 1 is 1 higher, and so on and so forth. So again, this is quantum mechanics, but rotational transitions. So finally, putting that all together, we can just calculate what delta J would be. So if you have, I took out this factor, and we're interested in delta J squared. So I kind of did a little bit of sloppy stuff here, but because it's hard for me to write on the board, I was trying to do something that would be visible, but also not take up an entire slide. So I took out, so this is essentially delta E. I listed it as delta J because I didn't want to write all of, it should say delta J squared, essentially. But it's just this bit subtracting J plus 1 from J. So this is J plus 1 is going to have J plus 1 times J plus 1 plus 1. And then we're going to subtract J times J plus 1. So our lower energy and our lower energy state and our upper energy state, just subtracting these 2 factors because this will be the same for both. Sorry, I got lazy. We can pull out the factor of J plus 1 because they're in both, and we end up with J plus 1 times J plus 2 minus J from here, which is the same as just saying 2 times J plus 1. Okay, so then plugging that into our equation for nu, we can see that it should be equal to the upper energy J plus 1 if we're transitioning from J plus 1 to J, J plus 1 to J. It's going to be equal to that divided by this factor. I might have missed a square. I think I missed an H squared. Sorry. And then because we multiplied by 2, that 8 becomes a 4. So that's a bit of quantum mechanics. We can get to the expected frequency for CO transitions if we're going from J+1 to J. So again, this might be, you'll use a CO J1 to 0 or CO J2 to 3, and those are just different energy transitions using this kind of quantum mechanics to get a transition. So lastly, I've gone ahead and I've plugged in a few values using that kind of iffy approximation of our carbon monoxide molecule as a bar, a massless bar with two weights on either end. So we have the mass of our carbon, the mass of our oxygen, and the separation between them. And when you plug that into our moment of inertia equation, you should get 1.4 times 10 to the negative 46 kilograms meters squared. And then when we plug that into our frequency equation, it should be 121 gigahertz times J+1. So for the different energy transitions, if you're going from 2 to 3, you'd plug in J equals 3, and you would get your frequency using this equation. This is slightly off because I made a few approximations, but it's pretty close to the frequencies we see when we look at the molecular gas. So that's how we get CO transitions. These are the frequencies we're measuring. You can, of course, turn that into a wavelength using speed of light equals lambda nu. So if you wanted to get a wavelength and work with that instead of a frequency, you just have to divide by the speed of light, or speed of light divided by nu. So when I talk about CO transitions, they're all rotational. This is what we're talking about. So that was a bit of hand-wavy quantum mechanics. Does anyone have any questions before we move to our next phase? So the next phase, we went cold molecular, now we're in cold atomic. So main difference in the cold atomic is that hydrogen, it's warm enough now that the molecular hydrogens are getting photodisassociated into atomic hydrogens, or bouncing into each other and turning into atomic hydrogen. But we're still at pretty low temperatures, 50 to 100 Kelvin. Density is still relatively high for the ISM, but really, really low for anything we might see on Earth. So 20 to 50 particles per cubic centimeter. Still really low in terms of our volume filling factor, so 2 to 4%. But the nice thing, and then again, we're going to be in kind of dense, clumpy clouds that are pretty well distributed throughout the ISM. Sorry. So really often we'll see atomic hydrogen emission from everywhere within a galaxy. So even though it's not much of the filling factor, because they're in these little clumps, those little clumps are everywhere in the disk. They're just really well constrained to the disk. So they're going to be really tight within the disk. We will see atomic hydrogen. The main way you measure atomic hydrogen is by looking for the 21 centimeter emission line, or looking for absorption depending on where you're looking. And a lot of times this line is used to measure the rotation speed of a galaxy by looking at the width of this line. Because it's going to be everywhere in the disk, you can look at the width, the Doppler broadening, and get a rotation speed. So we will do that in the second half of the semester. And just as a bit of a reminder, that 21 centimeter transition is that forbidden line, and it occurs when you have a spin flip from your spins aligned in your hydrogen atom, their proton and electron spin aligned, to the lower energy spins not aligned. So spin aligned, spin not aligned, and you get a 21 centimeter emission there. And there's the whole, we call it forbidden because it only happens like every 1,000 years if you just have hydrogen, but if you have enough hydrogen molecules, which we have a ton in a galaxy, you'll see enough of this that you can measure it pretty regularly because it is happening. So forbidden just means rare, but if you have enough, then rare becomes frequent. So we see 21 centimeter emission. So a little bit of practice with this. I might give you some hints, but I want to see if y'all can calculate. What would the speed of a hydrogen atom be in the cold atomic gas if we're looking at gas with a temperature of 30 Kelvin? So not going to put us in breakout groups yet, but what do we need to use? What equation might be useful here?
Ideal gas law.
So we're not quite ideal gas law. We're going to assume that we're in thermal equilibrium, if that helps. So everything's bumping into each other and we've reached, all the atoms are moving at the same speed.
A root mean square of velocity, like the square root of 3 kBt over m?
Yep, exactly. So we're gonna, let's see if I can do this. We want to use V, ooh, that's really big, okay. R, M, S equals 3, ooh, that's a 3, okay. K, T over M. So this is just assuming a Maxwell-Boltzmann speed distribution, which we can do because we're in thermal equilibrium. I've given you K and T and M. So if someone is able, you're all at computers, so I know you all have Wolfram Alpha, even if you don't have a calculator. So if someone can plug that in and shout out a velocity.
What's the 30 Kelvin dust 9.7 times 10 to the negative fifth meters?
Yeah, so I wrote it in microns, so I got 96 microns. So, but we're looking at kind of microns, so far infrared, especially for that warm dust. Did anyone try 100 Kelvin?
29 microns?
Yeah, so yeah, I wrote down 28, but I might have rounded. Yep, and other people are getting that too. Cool, so specifically, we often look at 24 microns to look at dust, just based on what temperature it typically is and using this black body radiation. But that's kind of what you can see. It's maybe slightly hotter than 100 Kelvin, but depends on where in the ISM you are. So just as you go into your activity, know that 24 micron, 20-ish to maybe about 100 microns is going to be looking at warm dust within the ISM. So now it's time for you to get to use all of the information I just poured into your brains to try to analyze some images of the Milky Way. So on Canvas, if you go to your assignments, hopefully you can see that there's something called Day 9, the multi-wavelength Milky Way. And that'll just have, it'll have both a link to these images. They're semi-small, but because the Milky Way is really long and thin, it's kind of hard to get better images. So this is the Milky Way from radio to gamma ray. And then I've also given you a little discussion quiz, which has some questions for you to answer using those images. So I'm going to go ahead and open some breakout rooms, and we're going to work on this for about 15 minutes. I have a little thing to share with you at the end. Okay. So if you didn't quite finish, if you could try to work through at least through question 5. Question 6 can kind of be a bonus. Were there any questions that people had that they'd like to ask the group? Any thoughts?
On question 6, we thought from reading it that maybe it was like a nearby pulsar, but we didn't know why there was such a bright spot.
Yeah, so the rotation of the pulsar creates magnetic fields, and that will energize electrons that can emit in the X-ray. I think that's the main part, but that was a little bit like of a, is it a question I got in one of my grad classes when I did a similar activity that I thought I'd throw at you all because you're smart and you can do it, but it wasn't quite as related to what we talked about today as some of the other ones. Anything else? Okay. And I'll look over your answers and I'll try to give you some feedback quickly on that. But I wanted to wrap up today by talking a little bit about DS9 and why you will need to use it. So if you have downloaded DS9, you should have something that looks something like this. And you can open DS9, which is the zip file that I unzipped, and it'll probably open some sort of terminal. And then eventually it'll open something that looks like this. You can also, if you're in a Mac, if you're used to working from command line, you can also open it that way. Let's see if I can move this without shutting everything down. Sorry. For the nerds out there, DS9 is named after Deep Space Nine, the Star Trek series, so it doesn't stand for anything besides being a nerd. Once you have it open, if you have an image downloaded, you can go to File, Open, and that'll let you open your FITS files. I don't want to go through all that. So I already have, this is just NGC 5866 in the U band from SDSS. The reason why you're going to need this is for those PSF calculations and for background subtractions. So the only thing you're going to need to do here is you're going to need to find your stars, and you're going to need to find blank areas that you can use for backgrounds. So one thing that's really useful is working with regions. So if you go to Edit and select your region instead of None, when you click and drag, you'll make a circle. So this would be a good circle to look at to find an average background value, because there's no stars there, there's only background. So when I double click on it, it opens this little box that has some information about that circle. Right now it's giving me the center of the circle in RA and DEC, but if instead I want to look at pixel coordinates, I can change this here to image, and that'll be an X and a Y position. So not super important for the background, but if you were looking at stars, this would be a really good way to get positions of stars that you could use for that PSF calculation. We can then find a background level by going to Analysis, just clicking on that, hopefully, sorry, and just hitting Statistics, and that'll tell you the value, different values within your region. So the sum of all the pixels in the region, the area, and then also the error, sorry, the number of pixels, all these kind of useful things. Our background value is going to be the mean value for your image in a blank region. So you just need to find a few blank areas and check what that mean value is, because that's going to be, if there was nothing there, if we didn't have the sky, if we didn't have faulty detectors, we would expect this to be 0. It's not, so the mean pixel value is your background. So in opening DS9, plopping down a few regions where there's nothing, and then using Analysis to get a mean value And you'll just subtract that from your aperture photometry before you convert to units. So this is in the same units as what you're doing in aperture photometry. You'll just need to subtract these values. So that's how you get a background. If instead, let me delete this maybe. If you wanted to look at where a star was, you could go, ooh, this looks like a nice circular star, and you can put your region down. And again, you can get a pixel location, which you could plug in, use the same kind of method we did to do the PSF fitting on the Spitzer image that you worked on last week. But I gave you a list of coordinates. This will just skip that step. You'll just plug those in directly. So you'll make a box around wherever your stars are. A kind of fun thing, if you want to test to see if your star is well fit by a Gaussian before, so you don't have to do this over and over again, you can use, if you go to region, you can use, you can change the shape to a line, and you can make a line across the star, maybe, there we go. And when you hit analysis and you've got a line, you can hit plot 2D. And if this shape is a nice Gaussian, then that tells you your star is well fit by a Gaussian and will be a good one to do PSF fitting with. Not something you have to do, but just an option if you want to test these out. And just shows that DS9 is a pretty powerful tool. It's kind of fun. If I drag this around, it'll move with it. And you could test different stars. You can move the galaxy. So the Python code we're using is a little different than what an astronomer might typically use, but DS9 is something that every astronomer uses pretty frequently. It's a really good way to look at FITS files. I think I also described this, but you can also look at the header from DS9. So if you just go to File, Display Header, that'll have a ton of information about your image in it, including, importantly, the pixel scale, probably, and the unit. That's one I can pull up. Aha, here we go. So the CD 1 and 2 are going to be your degree per pixel. Hopefully that matches what I said. If it doesn't, follow what I said in the instructions. Sorry. But that was all I wanted to say about that. So you should now have all the information you need to finish the photometry project. I will have office hours tomorrow if you are stuck, but there is still time. I think it's October 6th is the due date, so just coming up.